to you there some steady state data, some of the parameters. And then it states some assumptions, and really what I want you to focus on is just look through the model equations, and they're kind of broken into three subsystems. There's some equations to describe what's going on at the mixing point. There's an equation to describe what's going on in the CSTR, and there's an equation to describe what's going on in the separator. So in terms of the model, we're just tracking component A around the system. Okay, so the model focuses on component A, but what I want you to just do is spend a little bit of time talking amongst yourselves in your groups about how are those assumptions, how have they been incorporated into the model equations? Okay, so just so I get a sense of that you have an appreciation for how assumptions translate into model equations. So that's really just spend a few minutes on that, work through each assumption, and then we'll take that up, and then we'll go on to the next part. So you're doing part A. Trying to think about how each assumption has been incorporated into the model. So just spend a few minutes doing that.
What you missed is he uploaded a question on Quarkus called question 2, and we're going to be modeling that today. And right now he told us to go through the assumptions that he listed in the second page and to try to understand them. Then he's going to take it out as a class. Needless to say, I don't understand shit.
Man, that's an awful thing.
What'd you get?
Steak sauce, grilled onions, and lettuce. I'm really hating their steak sauce.
All guys are grouped of
4. But one person's not going to come today, and the one person, I don't know where he is. Yeah. Yes.
Kind of ruined my appetite.
It's actually that bad.
I'll wait till I'm finished.
Okay.
That steak sauce was all sour sauce.
So what happened is, Professor's not going to record lectures anymore. That means I have to record them on my computer instead, which is okay because I sit close enough to him, whereas I can catch what he says on the mic. But the problem is, I have to follow what he does exactly. Otherwise, the lecture video is not going to have everything he does. And that's a problem. I don't know, I feel like I can convince him to record them on his computer instead.
Okay, so process. Say you upload something like an
Yeah,
assignment.
it's on the tutorial site.
Oh no, yeah, I'll remember. It's okay because, yeah, it's okay. Yeah. Okay, so let's just work through these together.
Wait, we had past assignments. for
So start with constant molar holdup
That was one
M.
practice assignment.
this? Was it dudes?
No, it was just
So M is the total number of moles in the CSTR at any instant in time, and X2A is the mole fraction of component A inside this well-mixed CSTR. And we're making the assumption that molar holdup is a constant. So where does that come in? Where do we make use of that assumption? Yeah. That's right. So our accumulation term, the general accumulation term, is the change with respect to time of the total number of moles of A inside the reactor at any instant in time. So that's expressed as M, which is your total number of moles times X2A. You have to take that product derivative. If M is constant, then we can pull that out. Okay, if M is not a constant, then you have to apply product rule to open that term out, right? Because then both M is changing with time and X2A is changing with time. But if M is assumed constant, we can pull it out. We can divide through by M to produce equation 2. So what about all molar flow rates remain constant? How is that getting used? So in this problem, all the molar flows, M, F1, F0, F5, what are the other ones? Is that it? F3. Yeah, those are all of them, I think, are assumed to be constant. The only thing that's changing are the mole fractions. Yeah. Pardon me? So how are we using all molar flow rates remain constant? How has that been used in this model? Yep.
There's no dependence on time for the flow rates.
Correct. Yep. And what equations make use of that fact? I mean, the mixing equations, the separator equations, the CSTR equations, in general, those flow rates could be functions of time. So have we made use of the fact that they are assumed to be constant in any way, shape, or form in those equations? Yeah.
In equation 2, because it's a relationship with time.
Equation 2?
So CSTR.
How did we make use of it?
The relationship with tau is the factor of the data. You assume that that is constant because you can replace it with the level of tau.
That's right. So once you replace M over F, once you replace M over F1 by the constant tau, what is tau in this? What is it tau in this case? What do we refer to that tau as? What is M over F? It's 1 over 2.7 units of time, residence time. It's residence time. And because it's assumed to be a constant, that is where we make use of the fact that the F1 anyways is not changing with time. Otherwise, then you have to leave it as variable. You can't replace M over F by a constant tau. You have to treat F as a variable. So therefore, residence time is a variable. Okay. So that's correct. Thank you for that. Perfect separation unit. Let's take them in two parts with infinitely fast dynamics. So first, where have we used the assumption of a perfect separation unit? Yeah.
In equation 3, all of component A.
That's right. All of A goes out the top of the separator. Okay, so there's no A going out the bottom of the separator. So that's where that. And what about infinitely fast dynamics? How have we somehow used that in our? Yeah, Jeff. That's right. So the separator equation is just a simple algebraic equation. A going in equals A going out. So we don't have any accumulation term. So when you assume there's no accumulation taking place, in other words, when I change the input, the output changes right away. That means you're kind of ignoring the dynamics. And in a real separator, are you guys studying distillation in 311? Have you started distillation? Yes, no? No? Or yes? When you start modeling, for instance, distillation, which is kind of a classic separation unit for chemical engineers taking advantage of difference in vapor pressures to separate compounds, you start by writing a model for a single stage or a single plate. And you do like a mass balance around a single stage. And perhaps an energy balance around a single stage. And if you have 30 plates in your column, then you have 30 sets of differential equations that need to be solved for in order to figure out what's going on. And we'll see that when we get to Aspen dynamics. We'll work with the distillation column and you'll get a sense of how many equations, differential equations, are actually being used to represent, model, simulate, solve. And you can see our separator equation is so simple. It just says whatever goes in comes out. It doesn't account for any of the fact that there would actually be time required for a change coming in to be felt, if you like, at the top of the column. So it's a very gross oversimplification. Assumption 4, no transportation delay between separator and feed recycle mixing point. How about someone from the table over there, you guys? Yeah. Someone from that table. I should have numbers, like table number 3. Yeah, you guys over there. Hello? Yeah, you guys, you're going to answer this question for me. How do we make use of the assumption that no transportation delay between separator and feed recycle mixing point? How about you guys help them out? Right here. Yeah. No transportation delay between separator and feed recycle mixing point. Anybody there?
Well, I think that X3 would be the same, so you can use that as especially in the mixing point calculation of or in Formula 1.
Yep.
So there would be any time delay.
Right.
And you can assume that they'll be that same.
That's right.
At the
Exactly. So the fact that we use X3A as the mole fraction leaving the top of the separator, and you notice in the mixing equations, we use the exact same X3A as the mole fraction going into the mixing point. From a steady state point of view, that looks totally reasonable. But if you consider dynamic effects, then you really should be taking into account the time it takes for a change in X3A coming out of the separator to reach the mixing point, as we talked about yesterday in the context of time delay. So that assumption has been used by using X3A in both places, as stated by that table. And lastly, the isothermal process. Maybe we'll take another table. You guys over here. I should do like at weddings where we have a little pedestal with table numbers. So yeah, over there. Anybody from that table? How do we make use of the fact that we've assumed one of the things we can say is that we haven't included any energy balances in modeling this system. So the fact that there's an absence of energy balances, which could be obviously performed around each of the 3 subsystems, are absent. But there is something here on the mass balance side as well. Yeah.
Because the rate constant is constant.
That's right. So we're treating the rate constant as a constant. And hence, that's where we're making use of the fact that we're assuming isothermal behavior. Otherwise, that rate constant K0 would be a function of temperature. And in addition to that, we would also need energy balances to make sure we understood the behavior of the temperature enthalpies associated with all these streams would have to be taken into account. Okay, so the next part is a little bit of pencil and paper work. What I want you to do is question B, find the missing steady state data in the model equations. So I give you some of the steady state data, but not all of the steady state data. And the main things we're after here are X1A, X2A, and X3A at steady state. You're only given XAI at steady state. You're only given what's going into the entire system at steady state, 0.95. But I'd like you to solve for the other 3 mole fractions, X1A, X2A, X3A. And I'll come back and ask that table for some of the information, so you guys sort that out, and I'll get you guys at the back corner there to give me a piece of information, and you guys right in front to give me a piece of information, okay?
Okay, so we're saying find the missing steady state data in the model equations. Alright, I'm gonna mute the video for a second because I don't want to hear people. I don't want people to hear the dumb shit I'm gonna say. So. Okay, unmuted. Now everyone's gonna hear what we say.
Okay, we'll take this up in a few minutes. The main things we're after are X1A steady state, X2A steady state, X3A steady state.
Yeah.
Okay, I understand that, but I don't know how to do it, so I'll just wait for him to take it up.
Fret not.
Fret not. You know, if people are going to be watching these videos that I upload, I could be saying a lot of stories about myself and people are going to listen.
Yeah.
Like an actual YouTuber.
You could be talking shit and people would hear it all.
I'm not talking shit, like all the interesting shit that happens in my life.
Well, I mean, like, come on, man.
Even better, I can become like a inspirational speaker, you know? Like, yeah, motivate people. Like, you can do it, guys.
Okay, by the way, we gotta work on this assignment. It's one, like,
We do, but not today because I have to study for the quiz, and then after that I have to do my lab report. Over the weekend, most likely. Is that okay?
We'll do it Friday night. It's the first.
Possibly.
Okay, let's take you guys over there, X1A,
Well,
X2A,
before
X3A.
Friday, after separation.
Any one of them is fine. Go ahead. Pardon me? Still setting up the equations, okay? You guys over there have a number for me? You got one for me? At the back wall, still working? Here, still working? Okay, give you a few more minutes.
Oh, just like.
So you should be working with all algebraic equations. The only time derivative is the CSTR. So you set that to 0, and then all other variables get set to their steady state values.
Oh, that's right.
So you have 1, 2, 3, 4 equations.
The CSTR is not
And four
changing all the
unknowns.
time, so.
That is
1
true.
flow rate and 3 mole fractions.
Okay, you can attempt
Does
this.
someone have their hand up? Do you have one for me?
But I'll still wait for him to do it anyway.
Yeah, just confirm the answer.
I'm not confident. Why aren't you doing this? Why aren't you doing this?
Doing what?
No, like writing it out.
Oh, because it's simple.
Yep.
0.397.
0.397. I'm not sure that's correct. Anyone else have an X1A? I want them in fractions. 703? No, I don't think so. Huh? 2/3? That sounds more like it. Anybody else? Anybody else? Thumbs up? Thumbs down? That was X1A, was it? X2A? X3A? So what do we have here? We have the first equation is F1 equals F0 plus F5. F1 is not given, but F0 and F5 are given. So F1 is 2.7 moles per unit time. And then from there you want to solve for the 3 mole fraction. So do you have the other ones there?
1/3.
1/3 for X2A? Anybody else? Did you get the same? Anybody else? Yeah. Okay, so I've got 3 students confirming those values. Did you guys check yours, Claire? The fellow behind you there, I just want to make sure you guys are, did you check these? You don't agree? Claire, you agree? You're getting 1/2 for X3. Okay, so that's confirmed. Okay, let's go with that. So these values you'll see those are relevant because in the assignment I am going to get you to plot. We're going to look at what all the mole fractions are doing in the entire system. So we'll eventually do a subplot 4-1 where we'll look at XIA, 1A, 2A, and 3A. So we want to know what the values of those mole fractions are at steady state, and then obviously also solve for them in a dynamic way using the model equations. So what we're going to do next, again, this is a little bit of pencil and paper, and then we'll be ready to do some Simulink work. What we're going to do is develop transfer functions for the individual subsystems. So we're going to break the model down for the entire system into 3 subsystems. And what I want you to help me do here is, first of all, identify. I've sort of drawn the block diagram so that it kind of resembles the with recycle case. So it's kind of leading you on, so to speak, as to how we might identify these transfer functions. So for instance, if you look at the block diagram, you see that G1 is a transfer function that relates X1A to X2A. So what in the PFD, process flow diagram, relates X1A and X2A? What physical piece of equipment does that? CSTR. So you're going to use the CSTR equation to develop G1. Now G2 relates X2A and X3A. So again, comparing to the PFD, what piece of physical equipment is captured by that transfer function? X2A to X3A. Anybody else? separator. So I would encourage you to use the separator equation to develop the G2 transfer function. And then the mixing point is a little bit different. The mixing point, if we treat it as a subsystem, actually has two inputs. It has X3A, which is coming back to it from the separator, and it has XIA coming in from the fresh feed. And it has one output, which is X2A, the result of the mixing. So you're going to use your mixing equation to help you develop together G3 and G4. Okay? So what I'd like you to do is start with G1, start with the CSTR equation, and let's develop the G1 transfer function. We'll work on that for a few minutes, we'll take it up. Then I'll get you to work on the G2 transfer function, and then the G3 and G4. So if you want to work ahead, that's fine, but I'll sort of, give
Yeah, I'm trying to do question 3. C, sorry.
I'm not exactly the best with transfer functions.
Yeah, neither am I. So, at this point, I don't even know how to do this stuff. So, probably gonna wait for him to do.
Okay, so it's just output over input is all it is.
Okay. So every transfer function is always output over input, right?
Yeah.
And if we start with G1, like he said, the output is X2A, while the input is X1A. Isn't that right? And then do we write X2A out, like in the equations that are given?
So the output for it's gonna be, the output is x prime 1 of a, and the input is x I of a and x3 of a.
It's not X prime 1 of A?
No, this is to get this, you're inputting this and this together.
Yeah, I get that, but I thought we were starting with this one.
Oh, if you start at that one, then it's x2 prime.
Yeah, that's what I was talking about. Okay, let's start with G1. I feel like that just makes sense.
Okay.
Because he also said it in that order. Okay. So transfer function is output over input. And that equals to x prime of 2a over x prime of 1a, right?
Well, you gotta write down the equation.
Yeah, we have to write these out in the form of like the CSTR equations given? I don't know.
Yeah, so you usually get y prime over u prime of s. But then I don't know what equations to use for those.
Oh, we would need the Marlin textbook, right? For the Laplace transforms?
Yeah.
Oh, right.
Then it's y prime of s over u prime of s. Or I think it's the other way.
You could open up the Marlin textbook, like I can on my computer, but I don't know what to look for and where. I need to recruit someone who's smarter at this stuff to help me record the videos.
Oh, sorry, Shaft. Yeah.
No, that's not how I meant it.
Yeah, it is y prime of s. Okay, but then I guess what we can do for the next part is we can, since are we still working at steady state right now?
Yeah.
Okay. Then I guess you take the equations where you isolate for like the two variables and you put them on top of each other.
So how do we change it to the S domain?
Yes, it's that. Yeah, there you go.
Yeah.
Which in this case would be the output, which is
X2 prime A of S over X1 prime of A of S.
yeah,
Right?
yeah.
And that equals to G1. But then we would need to use.
So then in this equation, then you just need to
Okay,
solve.
let's take, let me take up G1. Actually, I know you have the answer there, so, you want to give it to me in its the form that you had it written down there? Like 1 over.
Oh, so
1
we
over
did it.
tau S plus 1 plus, yeah, I'll just write it as K naught tau. Okay. Now that's not in standard first order form. Remember, we need it is first order because the highest power of S in the denominator is 1. But if I want to put it into standard first order form, I need a plus 1 in the denominator. So I'm going to divide top and bottom through by what? 1 plus K naught tau, right? So the numerator will become 1 over 1 plus K naught tau over tau over 1 plus K naught tau S plus 1. Okay? So the gain of this transfer function is 1 over 1 plus K naught tau. The time constant associated with this system is tau over 1 plus K naught tau. So notice that the time constant is not equal to the residence time, okay? Because the speed of the system, the response time of the system is also related to the rate constant because we're tracking component A here. So rate constant kind of figures into the dynamics as well, which, you know, in a way you should expect that. Okay, now G2, you're dealing with just a algebraic expression here, so there's no kind of derivative to get you into trouble. I'll just quickly do this one with you. Some of you may have already derived this, so we still write the equation at steady state. So the methodology is the same. So the steady state equation is F2 x2a steady state is equal to F3 x3a steady state. And then as with the G1 case, you do a subtraction between the dynamic version and the steady state version. So it's really important you understand that first equation is a dynamic equation. I know there's no time derivative there, but remember I said that we assume the dynamics were infinitely fast. It is still a dynamic equation. In other words, x2a is a function of time. x3a is a function of time. So it is algebraic, but it doesn't mean it's the steady state equation. The steady state equation is when I replace x2a and x3a by their steady state values. Then that's the steady state form. If you subtract, you get f1 x2a prime equals f3 x3a prime. And then we can take the Laplace transform of that. That becomes f1 x2a prime of s equals f3 x3a prime of s. And the transfer function that we're after here, the output is x3a prime of s over x2a prime of s is equal to F1 over F3. So what kind of transfer function is that? Thinking of our library of dynamic behaviors. The first order, no. Second order, no. Yeah. Gain only. Gain only. It's only a gain. And this is how this very simplified model of the separator behaves. If x2a changes, say by a step, then x3a also changes right away by a step, scaled by f1 over f3. Okay? So real separators obviously don't behave like that, but it keeps things a little simple for today's tutorial. So based on that, go ahead and just get G3 and G4. The difference here with G3 and G4 is that you have really, looking at the subsystem, you kind of have two inputs, one output. So what you're looking for is an equation like this. X1a prime of S is equal to some transfer function G3 times x3a prime of S plus G4 times xia prime of S. Okay? So it's an equation which actually says this system has two inputs, one output. And so whatever is sitting out in front of x3a prime of S is what relates x3a prime of S to x1a prime of S. And whatever is sitting out in front of xia prime of S is what relates that to x1a. Or another way of thinking about it is to develop the x3a transfer function to x1a, you can kind of assume xia is not changing. And then to develop the xia to x1a transfer function, it's sort of like assuming x3a is not changing. So you sort of treat them as two independent inputs. So just take a few minutes and develop expressions for G3 and G4, and then we'll move over to simulate.
Do you know how?
I have an idea.
Good, that makes one of us. All right.
Which part are you trying to solve for?
G3 and G4.
G3 and G4. Okay.
I'm actually so behind in this course, now I realize. Because I can't do any of this math. That's so stupid.
Wait, where the hell is G3 and G4?
Yeah, on the left. So,
Okay.
we can write x3 prime of A, and xi prime of A out, right?
You're adding
This is what you said in the beginning, yeah.
Huh?
This is exactly what you said in the beginning. If we were to start with the mixing over here.
Yeah, you just add them together. So it's G x3 of A plus G4 xi of A.
That is
equal
true.
to x1 S. So then if you were to, I guess you would want to, that's hard. G4 and G3, so they're different. And you probably can't just take out, you can't take out G4 and G3 by themselves. So.
We want to find G3 and G4, so then we would have to find them independently first, right? Like, we have to find one of them on its own, then use it to find the second one.
Awesome.
So would we be able to find, let's say, wait, can we not solve for G2 first? And then using G2, we can solve for G3?
Yeah, we could.
The approach for the mixing point, just because I want to move along, it's really important you guys make sure you know how to do this. But I want to get to the simulation work so we can see that this is sort of the preliminaries. So again, we're dealing with the mixing point is an algebraic equation. There's no derivative there. Okay, so we really are going to proceed very much like the way we did with the separator. We just write the steady state form of the equation, F1 x1a steady state equals F0 xia steady state plus F5 x3a steady state. And then you're going to do a subtraction between those two equations. And I'll just jot it up here. Then you're going to get F1 x1a prime of t equals F0 xia prime of t plus F5 x3a prime of t. Then we can take the Laplace transform of that to give us F1 x1a prime of s equals F0 xia prime of s plus F5 times x3a prime of s. And then you're going to take, we're going to divide through by F1 here. So it becomes F0 over F1 xia prime of s plus F5 over F1 x3a prime of s. So it's an expression where there are two, again, just looking at this subsystem of the mixing point, we're treating x3a as an input to that, xia as an input to that, and x1a as the output from that subsystem. So the individual transfer functions are F0 over F1 and F5 over F1, gain only. So we've got four elements in this, four transfer functions that we're going to use for simulation. So we're going to switch to simulate now, and I'll show you how we're going to build that. We'll just work along side by side together on this. Okay, so you can open Simulink, open up a blank, open up Simulink, open up a blank model. If you have any questions, I'll just move through sort of at a steady pace. Put your hand up, Mitchell will get around to you. Open up the library. And start with the continuous library. Let's put a transfer function block onto our page. What we'll do is we'll build the block diagram first, then we'll go back and fill in the parameters or constants associated with each, and then we'll do the numerical methods, and then we'll do the simulations. So the other three this is obviously what we're going to use for G1. The other three transfer functions are gain only. Now I know we said in class that a gain only is like a special case of first order where you let tau go to 0, time constant go to 0. So in theory, we could simulate using a transfer function block with a 0 time constant, but numerically or computationally, that's not a good thing to do. You can get, errors. So what we're going to do is instead is use what's called a gain block. So if you go to commonly used blocks, you'll find this triangle called gain. So we want one of those. And you might want to build the block diagram so it kind of looks like for instance, the standard way the block is shown is inputs come into on the left and they go out on the right. But in this case, we might like to say, well, maybe we'll orient this kind of like the process flow diagram. So you can do a right click, rotate and flip, and I'm going to rotate it counterclockwise once. So that'll be our separator. Then we want 2 more of these. And you may want to, again, this one I want to rotate back clockwise. And this one I want to maybe flip it. And we need one summing junction, so in the same commonly used block library, we can grab a summing block, bring that onto the page. And then we can start making the connections. So G1, the output of G1 is the input of G2. The output of G2 is the input to G3. And then these come together for the mixing point here. Oops. Okay, so something like this. Now the only true input variable for when you look at the entire system, the only true independent variable is XAI. X1A, X2A, and X3A really are all dependent variables. Okay, when you step back and look at the entire system, I know when we were looking at subsystems, we were thinking of X2A as kind of an input to the separator, X3A as the output of the separator. Like when we looked at the mixing point, we said X3 was like an input to the mixer. But when you step back and look at the problem as a whole, the only independent variable is XIA. And everything else flows from that, or is governed by that and the equations. So we only need one source block, which will drive the simulation. So if you go to your source library, and let's put a step block there. And connect those up. So now let's go in and put in the parameters of the 4 transfer functions. So I just need your help because we need the numbers here. So what we need is an expression for 1 over 1. We need numbers here. 1 over 1 plus k naught tau. So that's 1 over 1 plus 1. Right? Is it 1/2? 1/2, everybody okay with that? So I'm going to just put in 1/2, and you can, sometimes it's helpful to put it in this way, then actually when you come back and look at it, we could put 0.5, but the fact that it's 1 over 2 may remind you that it was 1 over 1 plus k naught tau that determined that. Your denominator, so we now need tau over 1 plus k naught tau. So tau is so what is that value? Someone want to help me?
5/27.
What is it? 5 over 5 over 27? Or 0.5 over 2.7? Or 1 over 5.4? Right? Those are all the same number. Yeah. Is that correct? Am I doing it right? So 1 over 5.4 is what I'm going to put in. Okay? But if you're wondering where that comes from, this is tau over 1 plus k naught tau. And I'm just plugging in the values for k naught and tau that we've been given. Okay, that's okay. Now, and we can always make the block a little bigger if you want, so that it shows the parameters. So let's do G2 next. So what did we say G2 was? F1 over F3. So F1 is F1 is 2.7 over 1.8, is that right? 2.7 over 1.8, so again, I would probably put it in like that. Again, you could do the division, but then you'd forget where the heck did this number come from. It's more likely you're going to remember it if you see 2.7 over 1.8. Let MATLAB do the division for you. Next, G3. Again, I can make this a little bigger so it shows me. So now G3 was F5 over F1, is that right? So that's 1.7 over 2.7. Is that right? 1.7 over 2.7, thank you. So 1.7 divided by 2.7. And last but not least, G4, which is F naught over F1. So that's 1 over 2.7. Okay, so all transfer functions are in. Now, if you read down the assignment a little bit, or the question a little bit, you'll see that we're eventually going to want to do a dynamic simulation introducing a step change in XIA from 9.95 to 0.96. Now remember, whenever you're dealing with transfer functions, we're always in terms of deviation variables. So in this simulation, because we've used transfer function representation, then we have to put the change in XAI in its deviation form. So in deviation form, the initial value is 0 and the final value is 0.01. That corresponds to a change in XAI from 0.95 to 0.96 after you subtract 0.95 steady state. We can leave the step time as 1. That's a somewhat arbitrary thing, but the simulation here is. So that's in. Let's go, we want to eventually plot all 4 mole fractions that would be possibly measurable. So if you go to your sync library, we're going to use workspaces. So we're going to capture XAI. We also want to capture X1A. We want to capture X2A. And we want to capture X3. Okay, so again, I encourage you to change the names so they're sort of meaningful. So I'm going to call this capital X AI. It's a deviation variable, so if you want, you can call it prime. And remember to change the save format on these to arrays. Now, before we go any further, the assignment actually asks you to plot not the deviation variables, but the original variables. So what I've got here going into the first workspace is actually the deviation variable, not the original variable. So what do I have to do to the deviation variable to make it, to turn it back to its original variable form. So if I have the deviation variable, what do I do? I add the steady state value. So I'm going to correct my mistake here, and I'm going to put a summing junction here. And from the source library, I'm going to get a constant block. So we're going to combine the constant and the deviation to produce the original variable XAI. So I can actually rename this XAI now because that's what I'm going to save as the original variable XAI. And then, so this is XAI prime, and I want to add to that XAI steady state. And the steady state value is 0.95. Okay, so configure all the
Is that another step?
It's a constant.
workspaces in the same way. You want to, this is one of the reasons, for instance, that we started out by calculating the steady state value for X1, A2, A3A, because we're going to use them right now. So this one I'm going to call XA1. Switch save format to array. And then we need to put in the steady state value for XA1 here. And what did we say that was again?
2/3.
Thank you. 2/3.
What is that? XAI.
Just keep going. Do the same here. This is XA2. Save format, switch to array. And then we need to put in the steady state value for X2A. And this is 1/3, I think.
Yeah.
And we have one more to do up here. This is XA3. And then XA3 steady state 1/2. Okay. So that's the simulation. We've got our workspaces. So the last step is the numerical methods. Before we do a run. So we go to the gear, bring up configuration parameters. So the units in this problem aren't like given. I mean, I just say that the units of time are just simply time. so the default simulation is from 0 to 10 time units, whatever the time unit might be. And we're introducing the step change at time 1. So if we were to try to guess how long this system would take to reach steady state, what might we do? Well, the only transfer function in the entire system that has any dynamics is the reactor. So a reasonable thing might be to say, well, okay, let's just look at the time constant of the reactor. Because the separator and the mixing point don't have any dynamics. They are just algebraic equations leading to gain-only transfer functions. What's the time constant of the reactor? What's the numerical value? We said it was 1 over 5.4, which is, call it 1 over 5, about 0.2. 4 tau, about 0.8, around 1. So a reasonable kind of ballpark estimate of how long the system might take to reach steady state after we introduce the change might be about 1 time unit, just ballpark. So probably simulating from 0 to 10 is probably a bit more than we need. So let's go 0 to 5. And we always use fixed step. OD4 is our go-to solver. And I would never want you to use the auto. It's not a very good algorithm. And in fact, I'd always want you to choose this with some justification. So again, my rule of thumb here is look for there's only one time constant. Again, we said that time constant was up about 0.2. So I said you would not want to choose a value any bigger than 1/10 of that, so that would be 0.02. I'm going to err on the side of accuracy over speed. So let's go 0.01. Let's go 0.01. And now we're ready to run, so you can run that. And let's take a look at the workspace. So you should have a workspace similar to mine here. You have the 4 mole fractions. And T out, which automatically gets captured, is time. And why are they 501 by 1 vectors? We're simulating for 5 time units with a step size of 0.01. So that's 500 plus the 0 point is 501. So we're going to look at these results now. Probably best to develop a script for this. I mean, you can do it all in the command window if you want. But I'm going to put it in a script, and I would encourage you to use scripts. It's just more efficient because we're going to want to go back and use this script. So we'll do a subplot 411. This is what the assignment asks you to do. And then the order we do them, we're going to do plot T out, comma, X, AI on top. And then subplot 412. And then plot T out, X, A1. And then subplot 413. And plot T out, X, A2. Subplot 414. And last but not least, plot T out, X, A. And then let's run that script. Yeah. What do you want to say there? So just wait a minute till everybody gets this plot, because I want to walk through this, make sure we understand what's happening. Yep. All right. give everybody a minute to get that figure.
I wonder where I can get dangly earrings.
No,
I need a dangly earring.
okay, can I see your
Yeah. It looks like
Not,
this.
not that. I mean this.
Oh, this?
This side. Don't stop.
Also, like, I'm going to upload this video at some point, so you could just wait until then and follow along as I do it. That's the whole point of taking these videos, so that like all of us who are like stupid, we can look back at these videos and learn.
Alright. We'll just rewatch.
Exactly.
Where are you gonna upload?
YouTube, and I'm gonna make the video unlisted, so only people with links can access it. And I'm gonna post the links on the kind of TTO group. And hopefully, as like I go along, the quality of the videos improves. Like I figure shit out. Yeah. And also, like, I'll be able to like do the work that the professor expects us to be able to do. Like, right now, I wasn't able to do any of the math. Yeah. Your boy needs some catching up to do.
Like, I still don't know how we came up with that transfer function.
Pardon? Yeah, I don't know how to do the transfer function shit. Are we done? Or is there more actually? I wonder if there's more to do.
Oh, I'm just gonna try and finish this.
Can we dig question
So
E? I
let's
believe?
just walk through I want you to think about what's going on here, sort of as kind of chemical engineers, okay? So this course, one of my objectives is to get you to look at problems, sort of both from a chemical engineering perspective and also a dynamics and control perspective. So when I say chemical engineering perspective, it's sort of like what you've taken up to now, except this course. And then the dynamics and control perspective is what you've learned from 222 and now 322. Okay, that's what I mean. So as chemical engineers, maybe who haven't had a dynamics and control course, let's make sure we can understand what's going on here. So the inlet mole fraction changes from 0.95 to 0.96. The mole fraction going into the reactor changes at the same instant, but it doesn't step up as much as the inlet mole fraction. Inlet mole fraction changed by 0.01. Mole fraction going into the reactor, though, only changed how much? Certainly not 0.01, because that would be the whole scale there. So it's some fraction of 0.01, right? Something less than 0.01. So my first question to you is, why does the mole fraction going into the reactor not change by 0.01. Yeah.
Stream going into the reactor is also mixed.
That's right. So you have a mixing effect, or I call it a dilution effect. You have a stream coming back from the separator being added to the raw feed, fresh feed, and the mole fraction is only changing at this instant in time. It's only changing in the fresh feed. So that change doesn't translate into that mole fraction change in your feed to the reactor because of that dilution effect. Very simple mass balance type concept that you would have learned in second year anyways. Now, things start to change though. The inlet mole fraction going into the reactor starts to rise. So what's happening? Why is it going up? Why is the inlet mole fraction going into the reactor going up? Why doesn't it stay at this step value? Yeah.
Because downstream the same content gets reacted, gets passed on to the other reactor, and cycles back and comes in. So gradually, like it has a similar pattern.
Right. So what we have here, if you look at the third plot, which is telling you what the mole fraction coming out of the reactor is doing, you can see as a result of this increase in the amount or mole fraction of A going into the reactor, the mole fraction of A leaving the reactor starts to increase. Right? That's your third figure. And that increase goes to the separator, and then that separator increase comes back into the mixing point, and your concentration mole fraction going into the reactor starts to trend up as a result of that, right? Okay, so you're seeing that effect of the recycle start to kick in, right? And gradually this system reaches steady state. Gradually this system does reach steady state. How long does it take XA2, if you look at just the reactor, how long does it take the reactor outlet mole fraction to reach steady state? Roughly. How long does it take? Starts changing at time 1. Is it reasonable to say it's there at about 2.5? So it takes about 1.5 time units for the reactor to reach steady state. What was the time constant of just the reactor? It was 1 over 5.4, right? Which is about 0.2. So the reactor on its own, without any recycle, how long would it take to reach a new steady state if I set the input? 1 over 5.4, call that 1 over 5, call that 0.2. 4 times 0.2 is about 0.8 time units. But the reactor here takes 1.5 time units, almost double effect. And this is one of the most important effects that you do not see if you live in the steady state world. In the steady state world, chemical engineers love to do recycle, right? That's one of our main go-to things that we do, is a way of recovering and using unreacted material to try to improve your conversion and those kinds of things. We love to do that. But the downside, there's a cost to that. The downside is that on the dynamic side, the time to steady state for this system with recycle has increased as compared to if it was just the reactor on its own, which is really the no recycle case. Okay? So what we're going to do is a comparison with the no recycle case, just to verify that statement that I made. And the way we can do that, there's different ways to do this in Simulink. You could copy and paste this into a separate file, like you could create a blank folder and start again, or you can run simulations in parallel in the same block. So what I'm going to do is just copy everything we've done. And then just try to paste it down below here, see if that works. And you can actually run simulations, like you can have two models running basically at the same time. But before we run the simulation, we need to, what I want to do is rename the workspaces, because I don't want to overwrite the with recycle case. So first what we're going to do is do the modification required to do the no recycle case. And if you look at the process flow diagram, basically what we're doing here in the no recycle case is we're not taking any of that A coming off the top of the separator, and we're not going to return any of it to the mixing point. We're just going to send it all downstream. Okay, no fraction that is going to be recovered. We're going to just send it all downstream. In the block diagram, the way we can do that is just by or I guess we could just disconnect this. Okay, so I've now broken the recycle connection here. So we're coming off the top of the separator is X3A, but I'm not going to feed that back to the mixing point. Now, to make the two systems being the with recycle and without recycle, to make them identical at steady state, I actually need to introduce a secondary feed stream, which has the same steady state flow and mole fraction as the recycle stream is in the first simulation. So I'm going to introduce a step block here, because that actually now I've got a new input variable, which is the mole fraction of this secondary feed stream, which I'll feed into my mixing point. But in this simulation, we are going to just leave that mole fraction. I think if you go back to, just to show you the process flow diagram, so you know what I'm referring to here. So what I'm referring to in this diagram is the fact that to make these two systems identical at steady state, what I'm going to do is introduce, I'm obviously not doing any recycle. You can see clearly here the stream. None of that stream is going back to the mixing point. But to make the two systems equal at steady state, I'm introducing this new secondary feed stream called F5. And F5 will be equal to the flow rate coming back here, F5. And the mole fraction X5 would be the steady state value. The mole fraction of X5 would be the steady state value of X3. So it just means that what I'm doing is making sure that the two simulations have exactly the same steady state solution. So therefore, people can't say that if we see any differences between the two, that it's due to the fact that, well, you don't have the same feed flow rate, which would be a valid criticism of the comparison. So the comparison I'm doing allows for us to say, okay, the systems have exactly the same steady state solution. And so any effect we see here can be attributed to dynamics. Okay, so going back to the Simulink program. What that means is I'm cutting this off, and I'm connecting up this stream. But this mole fraction, when we do the simulation, the secondary feed mole fraction will not change. So this will be 0 in, 0 out. So in effect, nothing is changing with respect to that secondary feed stream, where of course in the recycle case it does change, yes?
Can you just put a constant there instead of
You could just put a constant there equal to 0, which would do exactly the same thing. Because this is a deviation variable. Because the simulation is in deviation variables. Right? Now, what we have to do is, I want to just make sure the workspaces are named appropriately but differently. So XAI, it's out of the 1, right? So what I'm going to do is change this to XAI NR for no recycle. And then this one, which previously was XA1, I'm going to change this to XA1 no recycle. Now this one over here was XA2, so I'll change this one to XA2 no recycle. This is just so it doesn't overwrite or create. And this one is XA. No recycle. Now we could put a workspace on this variable here, which is x5. Actually, it's x5a prime, but I'm not changing that variable. So if we did capture that variable, we would just add its steady state, and it would just remain at its steady state. So I'm not going to capture that because I know actually it's not changing. The only thing that is changing is, again, XAI. So we can run the simulation now. Should work. I might get an error message for my unconnected block. No, didn't mind. So down in my workspace, I should now have XAI, XAI-NR, and 1, 2, 3, 4. So again, if you created a script, what I'm going to do is just edit the script to include, in the same figure, to include the no recycle case. So I need a hold here, and then I can do plot T-out XAI no recycle. Now hold is a local command, it's not a global command, so you need to put hold into every subplot. And I'm going to change the line type as well, just so we can visually distinguish them. You can change color, you can change line type. I'm going to change line type. I think this changes it to a dotted line. And I should do that up here as well. It's XA1NR though that I want. NR. XAI-NR with a different line type. So again, I need another hold and plot T-out XA2NR with a change in line type. And then one more.
Oh, that's because we didn't change them to arrays.
Yeah, right. Yeah. Check that. If the time series will have that little clock symbol, but this is an array, so it's just 4 squares.
So this is the plot. Okay, I didn't put a dotted line in there. Rerun that. Forgot.
It's 2D array.
Yeah. I fucked up.
So this is the plot that, Josh.
Okay, so I have the same thing as professor, but it's still not right. Pardon?
There we go. This is the plot you're trying to get. Okay, so just to give everybody a few minutes.
Sorry, what did you add at the very end? Figure? At the top?
Oh, I don't know. For some reason, when I ran it, it gave just the second set of graphs.
Oh,
So
that's
figure
happening to
just
me right
forces
now.
it to make a new figure.
That's what's happening to me right now, actually. And I wrote figure, but still.
But you have the dotted lines in there too.
I do. Then, how come I have straight lines? No. Oh, I think I know why. Over here, did you change anything?
No,
To the step?
it's just here though. That should still be, is that, just open that just to make sure. Yeah, no, that's what we want.
Oh, no, the only thing that I didn't catch is when you disconnected the recycle stream and you added this step change.
Yeah, which should, oh, there it is, yeah,
Yeah.
final value 0.
Okay, there
So
we
we're,
go.
so it's a secondary feed stream to make sure the steady state of the two systems is the same.
Yeah.
But the disturbance we're gonna introduce is identical, so we
Yeah,
only
there we go.
change
It's all good.
XAI.
Understood. Thank you.
Everybody okay with that?
That's good.
Yeah, why is my shit different? Okay, why? Okay.
Okay, I don't know how to use Snapchat. I'm stupid. I'll take a picture of me, sorry. Sorry.
Okay, let's talk about the results now that we're seeing. So let's make sure we understand what's going on here. So in my case, the dotted line is the no recycle, the solid line is the recycle case. So we have both cases up here. So in the no recycle case, you can see that the second figure, which is showing XA1, it changes initially by the same amount as the recycle case, right? Does that make sense? Does that make sense? In other words, at time 0 plus, after the change in XAI occurs, the change we see in the mole fraction going into the reactor is exactly the same. You're just coming through the dilution effect of the mixing point. And there has been no chance, obviously, if there was recycle, for it to come back around yet. So initially, that change is identical. But you can see in the no recycle case, there's no increase in A coming back around. So XA1 just stays at that level. So it's just a simple step change. Now let's look at the responses in the mole fraction. So the third graph is the mole fraction of A leaving the reactor. So that's XA2. And you can see that it comes up. And how long does that take to reach steady state?
Like 1.75?
Like it looks like it's around 1 time unit, maybe a little less than that if you back off to sort of this 98% value. But basically compare those two lines. On the third graph, compare the solid line, how long does it take to reach steady state, versus the dotted line. The solid line seems to take about 1.5 time units. The dotted line seems to take perhaps less than 1 time. Agreed? So the system with recycle is slower. The effect of the recycle has slowed the system down, meaning it takes longer for that system to reach steady state. So that is problematic in an industrial or practical sense, because if that inlet mole fraction XAI is a disturbance variable, then when that disturbance variable changes, what we would like to do is try to get the mole fraction coming out of the reactor back to its desired steady state. And believe me, if the system takes longer to respond to the disturbance, it's going to take longer to bring it back. Okay, so it's kind of a nightmare situation for the operator, because you've now made the system, by adding the recycle, the clever chemical engineer who put this recycle stream in has just caused problems for the person that actually has to operate the unit, because you've made the unit much slower to come back eventually to steady state. What's the other difference you notice between the dotted line and the solid line? Time to steady state's one thing. What else? There's one other thing you should be able to say, yeah, it's different. What? The gain is different. So in other words, for the same disturbance, same change in the inlet mole fraction of 0.01, the effect that it has on the no recycle case is smaller than the effect it ultimately has on the recycle case. So what we refer to this as a sensitivity issue. In other words, the recycle system is more sensitive than the no recycle case. So it has two effects. It makes the system more sensitive. In other words, for the same disturbance, it causes a bigger change. That's bad news for the operator. And for the same disturbance, it causes the system to become slower. Also bad news for the operator. Because the operator wants this system to work at steady state, and both of those features make it more difficult for him or her to get it back to steady state when a disturbance comes through. Okay, so that's a real key takeaway for this assignment, is the effect that recycle has. We'll study it more from a CHE322 point of view, but what I really want you to understand it today is, as a chemical engineer, you understand what's happening in these two figures. Okay, you don't really need to understand anything about, yes, we use transfer functions to simulate the system, but if you just step back from it, and if I just show you these results and the two process flow diagrams, I want you to be able to explain what's going on as a chemical engineer. Okay, as a chemical engineer, that is the key takeaway from today. And also the other key takeaway is that you don't get any of this information using just steady state analysis. This only becomes apparent when you study the dynamics. Okay, and hence why all chemies around the world do a course in dynamics and control, for this exact reason, that you gain an appreciation for some of these things you're doing in design that have an impact on dynamics and control. The last part of the assignment is actually to make the simulation a little more realistic, and this is where we'll finish up with. We're going to just. Oops, I got the wrong mouse here. What we're going to do is put in a little bit of little more realism into the simulation. Remember, I said that one of the key assumptions was we assumed that there was no transportation delay between the separator and the mixing point. So we're going to build in a little bit of realism, and we're going to put a little bit of time delay in there. So if you scroll up, I'm going to show you how we can do this. You want to go to the, I've got to open my library again here just a second. Go to the continuous library and grab the transport delay block. So there's 3 delay blocks. Make sure you grab the transport delay one and just bring this onto the work page. Now I'm gonna, because of the orientation, what I want to do is insert this like basically on the, between the separator and the mixer. So I'm gonna, let's get this oriented properly. So I'm gonna go clockwise once, clockwise twice. That switches it to the orientation I want, because what I'm going to do is you could disconnect lines and then reconnect, but if you can actually splice this right in. So if I take that block and hover it over right there and just drop it in. Oh, I didn't get it. There. And you can drop it right in and it'll splice it in, meaning that it essentially automatically does the disconnect and reconnect for you. So this is a transport delay block, exactly like what we talked about in class this week. This is simulating the effect of the fact that it's going to take time for material to flow from the separator along a pipe to the mixing point. And let's start by simulating a time delay of 0.5 time units. So you just change time delay here, default. Let's change it to 0.5. And then just run that simulation. And then let's look at that. And then run your script. Sorry. So this is the figure. This is the figure you should be getting. I'm just going to run it again. I'm going to just percent out the no recycle, just not to clutter the. Let's focus on the. Okay, so this is the figure that I'm after. See if you can get this figure here. And again, we're going to explain this. Try to explain this as chemical engineers. Okay? So just give you a few minutes to get that plot. Okay. So again, let's look at the results. XAI changes again by its step 0.95 to 0.96. The mole fraction XA1 going into the reactor does that initial step change. It's not equal to, it's less than 0.01 because of the dilution effect. And then it stays at that value. It stays at that value. Why does it stay at that value? We've got recycle here. Why does it stay at that value? Yeah. That's right. So you can see that the mole fraction in the reactor is changing. XA2, the third line, it's changing. And therefore what's coming out of the separator is changing, but that change hasn't reached the mixer yet. So it stays as a step until 1.5. Why 1.5? Why does it start changing at 1.5? Yeah. Because 0.5 is the transportation delay associated with when the change does come out of the separator, the time it takes to reach the mixing point. And then you start to see an increase. And you can sort of see what happens is that the response in XA2, for example, the third plot coming out of the reactor, sort of has this kind of ripple effect. It sort of responds, and then it responds, and then it responds, and then it responds, and eventually it reaches steady state. How long does this system take to reach steady state? Around 4.5, starting at 1, so a total of 3.5. Even longer. This is the nightmare of recycle in chemical engineering. You're now creating these systems that have these incredibly long times to steady state. Okay? And let's just, for fun, let's just rerun it one more time with a time delay of 1. So just change your simulation. Change this back to 1. Run it. And plot it.
Oh no. It's even longer.
So you can see that this system has even longer. Now we're looking at, starting at 1, it looks to be settling around 5. And you notice, you can clearly see this kind of effect where XA2 goes up, goes up, goes up. And if you're ever in I don't care what environment, if you ever see that kind of behavior, it's kind of a clue that there's recycle in the system. In other words, there's an effect that just keeps wrapping around and around and around and around. And eventually the system does reach steady state, but it takes a lot longer. And remember, the only dynamic element here, well, there's two. There's the CSTR, and we've added now the time delay. But sort of the whole thing combined creates a system that's very slow and also very sensitive. So anyways, those are the main takeaways. That's it for today, and we'll hopefully see some of you tomorrow morning.
So you want to work on it like Friday night a bit?
Yeah, we should. Alright, tutorial for...
So I'm just going to ask the professor. Professor, I was just wondering, you asked us to like find the thing or like where it's output over. Yeah, I was just curious, how did you end up like getting those transfers on? Like I didn't know how to come. Like I knew that it was output.